satisfied. N1, N2, N3 is there. Okay. Okay. Now, norm double mod of x is greater than or equal to 0 and norm x equal to 0 if and only if x equal to 0 is there. So, when the norm condition means, what is the norm? Already, we have discussed in the previous class and under lower classes, and also in the previous year, that is the real number part, real analysis part. What is the norm x? That is the square root of inner product of x and x. That is the norm definition. Simply, it is denoted by norm x square equal to inner product of x and x. Already, we are now we will discuss in the further session what is the inner product space and some other inequalities are there. But here, especially, already we have learned in the norm condition. So, according to their norm, that is norm x means here x being any one of the vector, that vector, just you have to see here, that vector here, that must be one of the real number. That real number is also is in linear space is there. So that's why when the first condition is norm x is greater than or equal to 0 and norm x equal to 0 if and only if x equal to 0. Okay. Second condition, double mod of alpha x. So double mod means that is the norm alpha x. That is the scalar multiplication in between the norm. First condition is N1 is non-negativity condition and non-negativity means the positivity condition is there. Okay. Second one, norm alpha x. Yes, norm alpha here, alpha being in one of the scalar. So that scalar treated as in the absolute expression is there. So that is mod alpha into norm x. Here the scalar multiplication in between their norm. Now we are representing as mod alpha into norm x is there. Here alpha being the scalar part. Now, when the third condition, triangle inequality. What is the triangle inequality? Norm x plus y cannot exceed the, yes, norm x plus y less than or equal to norm x plus norm y. That is the triangle inequality is there. When these three conditions are satisfied in between their norm throughout the vector or our linear space element. So first one is the positivity condition. Second one is the scalar multiplication between the norm. And third condition is the triangle inequality. When these three are satisfied, that is called a normal linear space is there. Now that is the third exam. Can also be treated as, it can also be written as when the first condition is already we have discussed is there. Norm x means is greater than or equal to 0 means that is the non-negativity. So throughout the length of the vector. So N3 is there. That is the third exam. Here the can also be written as x, y, z is also being the any three vectors in linear space. Norm x minus z can also be written as norm x minus y. We are taking in between x and z. Minus y and plus y is there. So that's why. So norm a plus b means norm a plus norm b. So that's why norm x can also be written as norm x minus y plus norm y minus z. And here norm x1 minus x3 in the similar part, replacing z by x3 and x by x1 is there. We are taking here. Now in between the norm is there. Okay. Now in the same manner up to n consisting of vectors, n elements we are taking here. Norm x1 plus x2 plus so on plus xn can also be written as cannot exceed the norm x1 plus norm x2 plus so on norm xn is there. So enter all the sum of the vectors is also in linear space. Okay. Suppose here in n small n equal to 2 is there, we are getting the n3 condition. Okay, that is the simple proved part. Okay, please stay on the line. Already we have discussed in the previous part real analysis. We have learned that is the definition of a metric space. So throughout we are taking in any two vectors here x and y. That is also treating as real numbers. So what is the distance between x and y? That is also denoted by d of x and y. So here d of x and y is greater than or equal to 0 by the above the definition. So according to that, here d of x y equal to 0. That is the norm x and y means can also be written as d of x and y is greater than or equal to 0. In the same manner, d of x y equal to 0. When the distance means x minus y, when the x minus y equal to 0, in the same manner, if and only if, that is the necessary and sufficient part, x equal to y is there. That is the first condition. So this is the positivity or non-negativity condition for the metric definition. Now, metric means that is the first letter is capital M. That's why that is the notion of the first condition of the metric is M1, and M2 is when the distance from x to y, it is in the same manner y to x is there. So from x to y distance and from y to x distance is also same. So that's why d of x and y equal to d of y and dx. Third condition, d of xy can also be written as d of x and z plus d of, that is the distributive part. We are taking in between the z is there, so that's why can also be written as d of x and z plus d of z and y for all x, y, z is also being the real numbers in a linear space, or capital X is there. Okay, here that is the simple definition of a metric. Now, number of times repeated here from the definition of, from the beginning part of linear space, we have introducing the definition is, of a metric space in real analysis. A metric, it is a real valued function. Students, listen carefully. So here the composition is D is the composition. Now it is defined from x cross x to R. Here the binary operation is small d. Okay. So here distance is also defined from, that is the binary mapping is x cross x to script R. Okay. Now then the distance is denoted by d of x and y is there. As the following three conditions are satisfied, that is called a metric. Okay, students, listen carefully. Now, here, that is one of the theorem. Now, according to these theorems, we will proving the part of normal linear space. There is no doubt. Okay. Now, according to the definition of a norm and the conditions of a metric space, now let us see this theorem 1.5.1. Now, this theorem simply the notion of the metric d of x and y equal to norm x minus y. Okay. Now here x be a normal linear space and d be the function. So that function is also the binary mapping is there. That function is defined from x cross x to script R, defined by d of x and y equal to norm x minus y. So here d means that is a metric. Okay. Now metric means where first of all, so we are given the condition is d of x and y equal to norm x minus y. For the defined the mapping is first of all, just you have to observe the given this statement. Now that is the simple proof. There are number of times from the beginning of this part, a number of questions is given. Maximum we will get the score out of 70 easily to get the 40 marks from the first 3 units. Okay, there is no doubt because that is the main introduction part. Okay. Now, here d is defined from x cross x to script R, defined by d of x and y equal to norm x minus y. That is the given condition. Now, we must prove that d is a metric. So, that function is defined from x cross x to capital R. That is the defined the binary composition of a mapping. Now, here d defined the part is also we will prove that is the metric part. So, first condition M1, so that is d of x and y equal to norm x minus y. That is the given condition. So, that's why by the metric definition, that is the non-negative part means that is greater than or equal to 0. In the same manner, when the norm x minus y is greater than or equal to 0 means, yes, that is x minus y is also defined in capital X. That is the linear part. When the d of x and y equal to 0, when at the same time, if and only if norm x minus y equal to 0, if and only if x minus y equal to 0 means x equal to y is there. So that is the second condition, M2. So d of xy equal to norm x minus y, that is norm of x minus y can also be written as minus of y minus x. So that is mod minus 1 into norm y minus x. So norm y minus x means that is an equivalent to d of y and dx by N2 condition. Okay, so when the d of x and y equal to d of y and dx. So M3 condition is we have norm x minus y can also be written as by the distributive condition norm x minus z plus z minus y. We are taking the in between the x and y, z is there. So can also be written as less than or equal to norm x minus z plus norm z minus y. for any x, y, z is being the capital X. From the definition of a metric, yes, that is, we have simple proved that is d of x and y equal to d of x and z, because norm x minus z means by the definition d of x and z. Norm z minus y means d of z and y by M3 condition. For x, y, z is being the capital X. So finally, d of x and y can also be written as cannot exceed the d of x and z plus d of z and y. That is the d is a metric. Okay. Now, this definition is called induced metric. Okay. Suppose this question is given in the final examination. Now, from the D is defined from x cross x to R. Here, x be a normal linear space. From the definition d of x and y equal to norm x minus y, prove that D is a metric is there. Now, ORR, d of x and y equal to norm x minus y is the induced metric. That definition is called induced metric. Induced metric is also a metric. Okay. In sometimes, that is the more properties are here there. From the induced metric, we will discuss the some other properties are there. D of x plus z and z plus y means d of x and y. For all x, y, z, these are three linear space elements or three real numbers in linear space. From the scalar multiplication lambda x and lambda y of the distance, that is scalar is also can be expressed as the absolute expression, that is mod lambda into d of x and y. Here, lambda being the scalar element given in the field. So that's why here x and y belongs to capital X. Now that third condition, now we will see here d of x plus z and z plus y can also be written as from the definition norm x plus z minus of z plus y. Okay, norm x plus z and z plus y means from the definition norm x minus y is there. Okay. Now here we are treated as this is z, not x is there. Please rectify this one. Please rectify this mistake. In your textbook is there because it is very blunder. Now that is the norm x plus z minus of z plus y. Okay. Now x plus z means that is the some x is there. Z plus y means that value is some y is there. So norm d of x and y by the definition norm x minus y. So we're replacing y by z plus y is there. So this is also z. So after the simplification, we are getting norm x minus y. So finally, we are getting d of x plus y and y plus x, x plus y and x plus y. Okay, that equals to d of x and y is there because by definition, norm x minus y equal to d of x and y. Now this is also, please rectify this one. D of x plus z and z plus y. This is also d of x plus z and z plus y. We are getting the value is d of x and y. This is also, please rectify this mistake. This is z, not y is there. This is z. X plus z and z plus y is there. This is z. Okay. Now, finally, we are taking any two scalars in between the distance d of lambda x and lambda y that equals to norm lambda x minus lambda y by the definition. We are replacing those values by the metric condition, induced metric condition. So induced metric, how to satisfy the induced metric conditions, or are explain the induced metric condition, any three are there. So these four are induced metric. From the induced metric, we have derived some other inequalities are there. That is d of lambda x and lambda y. That is mod lambda into d of x and y is there. Okay. Now this is the metric induced topology. Okay. Now we know that in a metric space, the metric induces a topology means when these conditions are satisfied, that is called metric topology or induced metric topology is there. Okay, that is the simple notion. Okay, at the same time, we are taking any one of the sequences there from the induced metric topology. That is called a norm topology on X. Induced metric topology means norm topology on capital X. According to that normal linear space of given the sequence is there, here one of the sequences is denoted by xn be any one of the sequence. Okay, already we have learned in the lower session what is the sequence. Here sequence is denoted by set of xn is there. Here n being a natural number. Okay. Now that sequence xn is belongs to capital X. It is converges to x. Okay. What is the meaning of sequence xn converges to x? So mod xn minus x is less than epsilon. That is the definition of converges. Convergent definition is limit xn equal to x. Here n approaches to infinity. That implies mod xn minus x is less than epsilon. For all n being a natural number and epsilon is always greater than 0, that definition is called convergent. Okay. By the definition of convergent, we are applying the induced topology. Please stay on the line. Okay. Okay, see this here. The definition here, norm xn, norm xn minus x is less than epsilon from the definition of convergence condition. Okay, here what is the norm condition? Here especially norm x minus x is less than epsilon. By the definition of convergent sequence, we are getting the norm xn minus x is converges to 0 because epsilon is always greater than 0. That's why here norm xn minus x is converges to 0 as n tends to infinity from the definition of convergent condition. Now we are applying here. Hello? Now just you have to see here. This is the from the induced topology. Now that is the given the condition. Given the condition is norm xn minus x is converges to 0 as n tends to infinity. Now here the norm is also represented as the inner product of the norm is defined from, this is one of the binary operation. Now in an inner product space, it is defined from x to capital R is there. Okay. Students, just you have to see here. Norm xn minus x. Now that is the double mod of the inner product. It is defined from x to R. It is a continuous function on capital X. Okay. Now that is also we have to we shall establish the following inequalities there. Absolute of norm x minus norm y from the triangle inequality condition can also be written as it is less than or equal to norm x minus y. Okay. For x and y belongs to capital X from the induced topology of a metric. So this is the another equation is there. Let x comma y belongs to capital X. See here. Let x comma y belongs to capital X. Norm x can also be written as we are taking the one of the element is y. Norm x minus y plus y is there. Now this is x minus y is one of the element and y is also another element. It cannot exceed the norm x minus y plus norm y from the definition of a from the M3 condition. So norm x or plus norm y converting into this side, norm x minus norm y is less than or equal to norm x minus y. So interchanging x and y. So we are replacing the x and y is there, minus of norm x minus norm y equal to norm y minus norm x less than or equal to norm y minus x. We are interchanging the elements of replacing x and y to x is there. So finally that value is an equivalent to norm minus of x minus y. So here minus means we are taking that element is one of the product is there, minus 1 being a scalar. So mod minus 1 into norm x minus y, where the absolute of the negative is positive. So that's why given that expression is norm x minus y is there. So finally, see this equation. Finally, minus of norm x minus norm y less than or equal to norm x minus y. So from the both equations we get double mod under norm x minus y, norm minus norm y less than or equal to norm x minus y from the third and fourth equations. Okay. Now finally, given the sequence converges to x, here norm xn minus from the in between the we are applying that sequence in their norm. So norm xn converges to, now it read as norm xn converges to norm x as n tends to infinity. So we are getting the value. Now this is norm is continuous. Okay. In examination, prove that norm is continuous means enter this expression. We have to applying in the given that question. Okay. Norm mod of norm xn minus norm x less than or equal to norm xn minus x. So xn converges to x. It means that norm xn minus x converges to 0 as n tends to infinitive. It follows that norm xn converges to norm x as n tends to infinitive. Finally, given this, thus norm is a continuous function. So students, listen carefully. In examination, define the norm from the induced topology. We prove that the norm is continuous. Norm is continuous means now we are applying, this is the proof. Okay. And given that question, just you must present this, this is the answer. Okay. From the definition of a metric and from their inequalities and induced norm topology, we are getting the one only, we are taking the one of the sequence given this linear space or induced metric. Now that is the convergence condition is mod xn minus x is less than epsilon for all n is greater than or equal to m and epsilon is always greater than 0. Here n being a positive integer is there. Positive integer means that is the natural number is there. Okay. So we are applying the first, second, and third equations. Finally, we are getting the fourth condition. Now, from the third and fourth conditions, we are giving the condition is norm xn converges to norm x. Now, finally, given that norm is a continuous function. Okay. Now, in the same manner, we are applying here vector under vector addition and scalar multiplication are also continuous with respect to the norm topology. This is also another question is there. Okay. Now enter these are all from the norm condition. We are applying under vector addition and scalar multiplication. That is the continuous with respect to the norm topology. Okay. Listen carefully. Now, here xn converges to x and yn converges to y. Now, xn plus yn. Xn plus yn converges to x plus y. And xn converges to x. And at the same time, alpha n is also one of the scalar that is also converges to alpha. Now, we are the product of scalar multiplication can also be written as alpha n xn converges to. So, alpha and x is there. At the same time, we are taking in any two sequences, the addition of any two sequence of their under vector addition that is also converges to, because xn converges point is x and yn converges point is y. That's why xn plus yn converges to x plus y throughout the sequential part. Okay, here xn, yn, there are two sequences in capital X. Here, what is the capital X? Under the induced topology, metric topology is there. Alpha and be a scalar sequence. Here x and y belongs to capital X. Alpha is a scalar. Now the condition is xn converges to. Okay, see here. Xn converges to x and yn converges to y and alpha n converges to alpha. It means that norm xn minus x is converges to 0. And at the same time, norm yn minus y converges to 0. And in the scalar part, now mod scalar is also represented in the absolute expression. Mod alpha n minus alpha converges to 0. That is the meaning of alpha n converges to. So here n is also approaches to infinite. Okay, now it read as n tends to infinity or n approaches to infinity. So norm xn plus yn minus of x plus y equal to norm xn minus x plus yn minus y. Now from the norm condition, we are writing, we can written as, okay, norm xn minus x plus norm yn minus y is there. So this is also from the inequality M3, from the norm inequality third condition, norm xn minus x plus norm yn minus y. At the same time, these are all converges to 0 from the above inequality. Now here the continuous condition is, what is the continuous? Norm continuous condition. Norm xn plus yn minus of x plus y is converges to 0, and at the same time norm alpha n xn minus alpha n converges to alpha and xn converges to alpha. This is the continuous point. Alpha n xn can also be written as in between alpha n x minus alpha n x and plus alpha n x. Here alpha n is common. Mod alpha n of norm xn minus x and mod alpha n of x minus alpha n minus alpha of x is there. Okay. So here norm, particularly here we are remembering that one of the point is there. Now here throughout the sequence and vectors, we are representing in between their norm is there. Okay. Okay, that is norm xn minus x is converges to 0 and mod alpha n minus alpha is converges to 0 as n tends to infinite. Hello? Can you hear me? Hello? Can you hear me? Okay. Now, here the condition is norm xn minus converges to 0 and mod alpha n minus alpha converges to 0 as n tends to infinite. It follows from the above inequality that norm alpha n xn minus alpha x is converges to 0 as n tends to infinite. Okay. Now, the vector addition and scalar multiplication both are continuous with respect to the norm topology. Now, this is one of the important concept is there. Okay, in examination that is also given, prove that under vector addition and scalar multiplication are continuous with respect to the norm topology. In sometimes that question is also given. Okay, don't forget this one. Now some other examples of throughout the normal linear space. Just you have to see and refer here. Okay. Now what are the examples of normal linear space for real numbers and complex numbers part? Okay. Now just you have to see and refer 1.5.2. This is one of the well-established example for normal linear space. Okay. Show that the real linear space scriptor is a normal linear space with the norm x is equal to mod x. So given the condition is throughout the norm x equal to mod x is there. Okay, here x being the real number, that is the scalar field is a scriptor. Okay, now what is the normal linear space condition? N1, N2, N3, these three conditions are satisfied according to the given condition. Now then automatically easily to prove, proving the part of a normal linear space under the given the condition. Okay. Okay, see here. We verify the three exams of a norm. First condition is norm x. Norm x equal to mod x. That is the given the condition. From the first condition of a norm, it is greater than or equal to 0. Non-negativity condition, that is norm x equal to 0 means mod x equal to 0. Then automatically x equal to 0. So first condition, it holds good. And second condition, scalar multiplication in between their norm. Norm alpha x equal to, now from the given the condition, replacing x by alpha x and the mod alpha x is there. Mod alpha x can also be written as mod alpha into norm x is there. Okay. Now here mod alpha into mod x means here again this is alpha being a scalar. So mod alpha into norm x is there. So second condition it is satisfied. Now here the third condition is, what is the third condition? Here x and y by any two real numbers. Here hence the condition it follows that norm x plus y cannot exceed the mod x plus mod y from the inequality of triangle inequality is there. So we can also be written as norm x plus y equal to mod x plus y. That is the from the given the condition. Less than or equal to mod x plus y means that is the sum of individual their modules. Okay, mod x means from the given the condition norm x, mod y means from the given the condition norm y. So N3 is also satisfied under the condition is N3 is norm x plus y less than or equal to norm x plus norm y is there. So then when N1, N2, N3, these three conditions are satisfied from the given the condition norm x equal to mod x, then automatically script R is a normal linear space over script R. So it will easily to show that it is easily to show that 1.5 with the 5.3 example throughout the complex numbers. Okay, to show that script C. So in the examination, prove that script R and script C is a normal linear space over capital C. So now we must present 1.5.2, 1.53. Okay, so here, through replacing a script R by script C, then automatically easily to prove N1, N2, N3 conditions are satisfied. That is called, that is called normal linear space. So N3 is there. X and Y belongs to complex numbers. Here, norm, mod, X bar and Y bar. There are two complex conjugates of X and Y. Bar denotes the conjugate expression. Okay. Now, then we have, just you have to see and refer, mod x square equal to, already just from the introduction of the complex numbers, and now we have introduced the complex number system. Now, mod x square means x into x bar and mod y square means y into y bar. This is the basic principles of complex number system. Okay. Now, therefore, mod x plus y whole square equal to, now this is x plus y is the z, x plus y and x plus y bar. So this is mod z square. Replacing x plus y means z is there. Mod z square means z into z bar. Replacing z by x plus y. So that is x plus y of mod x plus y bar means conjugate of x plus y. It read as a conjugate of x plus y. So that is the individual effort here. Sum of any two conjugates x bar and y bar. So can also be written as x into x bar and deviate of distributive property x into x bar plus x into y bar plus y into x bar plus y into y bar. And at the same time, from the condition x into x bar is mod x square. So enter this value less than or equal to mod x square. Y into y bar means mod y square. So xy bar plus y bar yx bar means 2 into mod x and mod y. So we are giving that. We are proved that here mod x plus mod y whole square. So students, this is also one of the mistake. Please rectify this mistake. This is mod x, not y is there. This is mod x. Okay, mod x plus mod y whole square from the above expression. So finally, it follows that mod x plus y less than or equal to mod x plus mod y, and that is the absolute expression. And according to the given the condition, we are applying the norm part, norm x plus y less than or equal to norm x, replacing x mod x by norm x plus norm y. That is the N3 condition holds good. In examination, this question is given. Prove that script R and script C is a normal linear space over script R and script C. Okay, this is that is the one of the question is there. Okay. So in the same manner, see this one 1.5.4. This is the n tuples of the real numbers over capital R. We are taking the n tuples means n dimensional of the linear space. So we are taking the vector n tuples of the real numbers throughout the dimension over the field of the elements are real numbers, and over n tuples of the complex system throughout the complex numbers of the field elements, both are also normal linear space. In the above expression is only one dimensional part is there. Okay. Now, but here we are applying replacing n by 2. That is the r square, two-dimensional part. Okay, that is we are taking two elements x1 and x2. N dimensional part means we are giving the vector is x can also be written as n tuples of the elements. N consisting of the vectors, that is x1, x2, so on, xn. Okay, now that is also this expression norm x with the norm x equal to maximum of mod xi. Norm x, given the condition is mod x and norm x equal to maximum of mod xi. Here I varies from in between 1 to n values. So that can also be written as here x can also be written as given this expression x1, x2, so on xn. Now this value can also be written as L infinite, n-dimensional part, okay, linear system of the infinite dimensional of and n tuples of the elements given this linearity. So that is Ln infinite, okay, it read as L infinite, n tuples of the L infinite, okay. Now here the proof, just you have to see and refer this proof. R power n means that is the normal linear space. Don't forget this one. We usually hear this expression norm x equal to maximum of mod xi. Here I lies between 1 to n is there. That expression denoted by L infinite of n. Okay, L infinite n is there. So n tuples of the, first of all, so we are taking the n tuples of the real system. So R power n, okay, n dimensional of the elements, that is also a normal linear space with the above specific norm is there. When the first condition n1 from given the condition is norm x equal to maximum of mod xi is also applying. So when the norm x equal to 0, then automatically norm x is greater than or equal to 0 means norm x equal to 0, and hence the condition is maximum of mod xi equal to 0. So similarly, mod xi equal to 0 means I varies from 1 to n. So here xi equal to 0 means simply that is x equal to 0 is there. So just in the specific manner, okay, norm x equal to 0 if and only if x equal to 0, that is the first condition holds. Second condition is norm alpha x. Now we are applying the condition, given the condition maximum of mod alpha x. So mod alpha x can also be written as mod alpha into norm xi. Mod alpha into maximum of mod xi means norm x is there. So n2 condition is also holds good. Okay. And in the same manner, the n3 condition is there. So maximum of mod x plus norm x plus y equal to maximum of mod x plus yi. That is the given the condition. So third condition is mod xi plus yi less than or equal to mod xi plus yi. Now we are applying the norm according to the maximal values. Norm x plus y is less than or equal to this value is norm x, this value is norm y. Okay, n3 is also holds good. Now, in the same manner, we are applying in the n tuples of the complex system, that is also a normal linear space. Okay, that is the simple proof. Just you have to practice here. You must practice the above expression. Okay, now this is called norm x equal to, the above value is norm x equal to mod x. That is called, okay, see this one. Okay, now it is also denoted by norm x equal to maximum of mod xi, that is called L infinitive of n. So that value is also called supremum norm. What is that? Supremum norm is there. Okay, it is called the supremum norm or maximum norm is there. So define maximum norm or supremum norm means norm x equal to maximum of mod xi. Now from the concept of from the basic concept of functional analysis, don't forget and don't deviate these points especially. Please, you must remember, given the condition, what is the norm, throughout the norm, how to explain the norm condition in various types. Okay, norm x equal to maximum of mod xi. Now here I lies between 1 to n values, that is called the maximum norm or supremum norm is there. Now these are all also that is one of the expression throughout the n tuples of the real linear space and complex linear space. Over the real numbers and complex numbers are normal linear space with the norm x equal to summation mod xi whole square and whole power 1 by 2. Now given the condition this is, and according to this condition, we will prove that is the normal linear space. So here first of all n1 condition. Now in the given this condition, just you have to observe here, norm x is greater than or equal to 0 means norm x equal to 0. So at the same time from the condition summation mod xi whole square equal to 0, or then automatically mod xi equal to 0. And again, simply xi equal to 0 means x equal to 0. Okay, first condition holds good. The same condition, second condition, norm alpha x equal to, given the condition, replacing alpha x by, from the given the condition, summation mod alpha xi whole square and whole power 1 by 2 is there. Okay. Now then automatically mod alpha into norm x is there. N3 condition is also, we are applying the, given the condition from the inequality, Minkowski inequality. Minkowski inequality, we are replacing p equal to 2 on behalf of that expression, summation mod xi plus yi whole square and whole power 1 by 2 less than or equal to summation mod xi whole square whole power 1 by 2 plus summation yi whole square and whole power 1 by 2 is there. Okay, now this value is equivalent to norm x and this value is equivalent to norm y is there. Okay, now here n tuples of the real system and n tuples of the complex space, here that is called n-dimensional Euclidean. This is called n-dimensional Euclidean. This is n-dimensional unitary space. Okay, now R power n and C power n, it referred as, and it is also called n-dimensional Euclidean space. This is called n-dimensional unitary space. Don't deviate here. So throughout the n-dimensional real and complex, both are normal linear space. That is also one of the question is given. So we have to apply 1.5.5 example is there. Now here that is 1.5.6 in the same manner. This example is also on normal linear space definition. P lies between 1 less than or equal to p less than infinite throughout the Euclidean space and unitary space on n-dimensional. It is also a normal linear space with the following norm is, here particularly in the above example is p equal to 2. But here norm x equal to summation mod xi whole power p and on the whole power 1 by p. That is also same. It was followed by the, from the above example. That is also same. Okay. This example is also very important in the final examination. These are all well-established examples for on behalf of normal linear space part. Okay. Now here, this is also R power n of the normal linear space is denoted by LP power n. This is the LP spaces on n-dimensional. L infinite on n. Already that is also explained here. But here P lies between 1 to infinite. P is lies between 1 is less than or equal to P less than infinitive. That is the condition of LP spaces on n-dimensional. So LP dimensional on n normal linear space in the examination is also one of the given. That question is given. So just you have to see and refer 1.5.7 is there. So LP, here P is greater than or equal to 1. That is a normal linear space. Okay. Now verifying the axioms of norm. Axioms means properties, laws, postulates, conditions. Now there are all similar names for the axioms. Okay. Now axioms of a norm means the first condition. Now given the condition is norm x equal to summation mod xi whole power p and whole power 1 by p. Here I equals to 1 to infinite. Here the first condition is norm x is greater than or equal to 0 and applying the given the condition, then automatically x equal to 0 is there. And in the same manner n2 condition and from the Minkowski inequality for sequences, we are applying the n3 condition given this example, summation mod xi plus yi, summation mod xi plus yi whole power p and whole power 1 by p less than or equal to summation mod xi whole power p and whole power 1 by p plus summation mod yi whole power p and whole power 1 by p. So p lies between 1 to infinite. From the condition of inequality, norm x plus y less than or equal to norm x plus norm y. Now these are all well established examples on norm definition. Please stay on the line. Okay. In the same manner, just you have to see and refer 1.5.8. This example is also same. Norm x equal to, this number of times is given. These examples are very important in the final examination. One essay question is given, one short answer is also given. Don't deviate here. Okay. First unit is very most important for your understanding purpose throughout the functional analysis. Okay. So 1.5.8, just you have to see and refer. L infinitive is also a linear, normal linear space. L infinitive means given the condition is norm x equal to from the given the norm x equal to supremum of mod xi. Now that is also we are applying for the sequences condition vector addition and scalar multiplication. X plus y means the sequence xn plus sequence yn, because sequence of xn plus yn converges to x plus y, and before that example already we have practiced for normal linear space. That is the sequence of xn plus yn. Alpha x, scalar multiplication is alpha of xn, because x is the convergence point. That convergence point for the sequence of xn is there. So okay, now that is alpha of sequence xn, that is sequence of alpha xn. So to verify L infinitive is a linear space over script R. So we are taking first of all our the assumption, suppose x equal to sequence xn and y equal to sequence yn. Now these are in the L infinitive part. Okay. Now here the applying the conditions norm x equal to supremum of mod xi is greater than or equal to 0. When the norm x equal to 0 means given the condition is supremum of mod xi equal to 0. Implies simply that is xi equal to 0 means I varies from 1 and 2. So x equal to 0, then automatically first equation holds good. Second equation in the same manner. Okay. Hello? Hello? Please respond here. The second condition is norm alpha x equal to supremum of mod alpha xi. So that is supremum of mod alpha into norm xi is there. Okay. Hello? Hello? Students, please respond here. Okay, can you hear me? So, here the condition is norm alpha x equal to supremum of mod alpha into norm xi is there. So, supremum of mod xi for the given the condition mod alpha into norm x is there. That is the second equation holds good. Then the third condition is norm x plus y equal to supremum of mod xi plus yi. Cannot exceed the supremum of mod xi plus mod yi. Now, that is in an individual effort is there, it cannot exceed the supremum of mod xi plus supremum of mod yi for the replacing of the given the condition of the values norm x plus norm y is there. So, N3 is also holds good. Okay. N3 holds good. So, L infinitive means, what is the meaning of L infinitive? Explain the L infinitive means the set of all bounded real sequences is a normal linear space. The set of all bounded real sequences is a normal linear space. That is the L infinitive part. In the same manner, set of all bounded complex sequences is also a normal linear space over complex numbers. Don't forget this one. L infinitive expression throughout the L infinitive, how to derive the normal linear space throughout the real sequences and complex numbers. That is the one of the finished example 1.5.8. See this one 1.5.9. Okay, these examples are also well established in the further concept, because suppose we will explain the Banach space. These examples are also concerned part of Banach space from the normal linear space examples. Okay, now so let us just you must practice each and every example throughout normal linear space just then automatically easily to understand in the further concept, that is the Banach space and some other also there. Okay, inner product test, these examples are also concerning of remaining part. Okay. Now, here the given the condition is throughout the norm f equal to, throughout the set of all bounded continuous functions is there. Throughout the linear space, C of AB equal to, there are set of all bounded continuous functions represented as C of AB. The script C of AB means it referred as the set of all real bounded continuous function of the part C of closed interval AB equal to, this is also one of the linear space. Set of f, g, h, there are the number of, but you are taking the f is there. F is also defined from interval AB to Kepler. This is the real valued continuous function of the mapping. F is defined from closed interval AB to R. Suppose you are taking G is there. G is defined from interval AB to R. H is there. H is defined from interval AB to R. So these functions are involved in the set of all bounded continuous functions. When this is also a normal linear space. In examination, prove that C of AB is a normal linear space. That is the simple. C of AB is a normal linear space. Hello? Sir, anduti sir. Nenu chestanu oka pavu. Okay. Now, here norm f equal to, this is norm f equal to supremum of mod fx. Okay. Here x is consisting of interval AB. So x being the element of in between A and B is there. So norm f equal to supremum of mod f of x. So here just see and refer this proof. C of AB is a linear space over capital R. We shall verify the exams N1, N2, N3 is there under given the given the condition. So the set of all real bounded continuous functions denoted by C of AB from the definition of norm f equal to, already C of AB is also now we have studied in the topology part. Okay, that is the previous paper 5 is there. Okay, now here norm f equal to, first of all, norm throughout the functions, norm f is also greater than or equal to 0. Norm f means absolute of the function equal to 0. Then simply f of x equal to 0. That is the entire part of necessary and sufficient part. If and only if is also you must mention here. F equal to 0 on closed interval AB. Simply f of x means simply notated as f equal to 0. So first condition it holds good. Second condition is norm alpha f. Norm alpha f means supremum of mod alpha f of x. Here x is consisting of interval AB is there. So it can also be written as supremum mod alpha into f of x. Okay. Now mod alpha into supremum of mod f of x. So finally mod alpha into norm f is there. That is the second condition holds good. Third condition is throughout inequality, triangle inequality, we are applying given the condition norm f plus g equal to, norm means a supremum of mod f plus g of x. Now that is can also be written as supremum f of x plus supremum g of x is there. Supremum mod f of x means norm of supremum mod g of x means norm g of x. Simply that is norm g is there. So the N3 condition it holds good. So finally, when N1, N2, N3 conditions are satisfied for given the condition, so that's why C of closed interval AB is a normal linear space over the real numbers. Okay, and it is also, it will be shown that throughout the complex numbers is also C of AB for the complex numbers, that is also a normal linear space. Replacing R by C is there. That is the simple proof. That is your practice purpose. Okay. Replacing script R by script C. So on the above example throughout the real numbers, this example is, that is the complex numbers of this part. So the above example is called uniform norm or supremum norm. Okay. Now in examination, this question is also one of the type is there. Now, the question is also given in the another way. Prove that uniform norm is a normal linear space. Prove that supremum norm is a normal linear space. Now, you must presenting in the final examination. Now, there is a 1.59. That is the C of AB is a normal linear space. That is called uniform norm or supremum norm. Students, this example is also just you have to practice 1.5.10. Okay, throughout the integration part. So this is also same. Norm given the condition is norm f equal to, now integral 0 to 1 mod f of x whole power p and whole power 1p. LP is a normal linear space throughout the integration. So given the condition is norm f equal to integral 0 to 1, the set of all bounded function on integration, integral 0 to 1 mod f of x whole power p and whole power 1 by p of dx. Here p lies between 1 to infinite. So this function is a norm on C of interval 0, 1. Okay, that is the same. When N1, N2, N3 conditions, we are applying for the given the condition, then automatically now that is also denoted by norm F equal to norm F means norm F at P. It read as norm F at P. P lies between 1 to infinite, 1 less than or equal to P less than infinitive. That is the set of all bounded functions on P part. Okay. So what about the condition P? 1 less than or equal to P less than infinite. Okay. Next, this one very important. Please stay on the line. This is the linear subspace. What is the linear subspace? That is the vector subspace. Already we have discussed in the from the beginning of the part in the functional analysis class. Yesterday already I explained here one of what is the subspace condition. Okay, that is a simple expression x plus y and alpha x. There are two conditions here, and NBA normal linear space and MBA non-empty subset of a linear space. Non-empty subset of a normal linear space, where then it is also called linear subspace. Hence, the following conditions are satisfied. There are two type test and one type test is there. Two type test means x plus y belongs to capital M and alpha x belongs to capital M. Here x plus y means under the vector addition, we are taking the any two elements throughout the linear space elements. X comma y belongs to M and x plus y belongs to M. Alpha being any one of the real number and x belongs to M, scalar multiplication holds good. Under vector addition is closed and scalar multiplication is closed throughout the linear space elements. So that's why same elements that is also is in non-empty subset. So that is not that non-empty subset is capital M. So M contains capital N is there. M is a subset of N is there. So that's why x plus y belongs to M and alpha x belongs to M. So here x and y both elements are is in or belongs to. It reads as is in or belongs to or consisting. It is consisting. Okay. Now there are so many references are there. Here x and y belongs to capital M and alpha being the field element. Now this is also called linear subspace or linear manifold. Okay. Linear subspace or linear manifold. This theorem is number of times is given in the final examination. The closure of a linear subspace of a normal linear space is a linear subspace. So first of all, you must understood the given the concept normal linear space of the linear subspace. Then it is closure of the part is also a linear subspace. That is for our reference part. Okay, first of all, so we are taking the normal linear space part is there. And according to the normal linear space, NBA normal linear space and MBA linear subspace is there. Then its closure is also a linear subspace. Then its closure is also a linear subspace. So this theorem is also very important. Please stay on the line. This is the proof. First of all, let M be a linear subspace. M is a linear subspace. Already explained here. So normal linear space is denoted by capital N and M be a linear subspace because M be the non-empty subset of a linear subspace. So that's why according to the condition x plus y and alpha x belongs to M. Now then easily to satisfy M is a linear subspace. So M be a linear subspace of a normal linear space N and M bar its closure. Now consider here x and y belongs to M bar and alpha being the field element. That is the scalar field. So by closure property, there exists a sequence, xn sequence, yn sequence. There are two sequences in capital M. So xn converges to x and yn converges to y. Then automatically, hello? Please respond here. Who is K? Hello? Students, please respond here. Okay. Now, vector addition and scalar multiplication are continuous. Already we have explained in the above part. Xn plus yn can also be written as xn plus yn can also be written as limit of xn plus yn is there. Please stay on the line. Okay. Now, Here xn plus yn, xn converges point is x and yn converges to y from the closure condition. Now closure of the elements are x and y. Same elements, linear space of the elements is also consisting closure of the subspace. So here alpha being the field element. So throughout the sequential part by closure property, throughout the sequence xn, yn, there are two sequences converges point is x and y. So it read as xn converges to x. Now it means that mod xn minus x is less than epsilon for all n is greater than or equal to m. That is the convergence condition. Throughout this condition, yn converges to y means now mod yn minus y is less than epsilon for all n is greater than or equal to m is there. So under vector addition and scalar multiplication, x plus y can also be written sum of the convergence points. X plus y equal to limit of xn plus yn from the condition of convergence. Okay. So individual of their sums, limit xn plus limit yn. So alpha x is limit alpha xn because x converges of the sequential part is xn. That's why it can also be written as alpha into limit xn is there. So finally, xn plus yn belongs to capital M and alpha xn belongs to capital M. So here x plus y belongs to m bar and alpha x is also belongs to m bar. Now this convergence point is x plus y belongs to convergence points in the closure expression. So that is x plus y belongs to m bar and alpha x belongs to m bar is there. So finally, given the m is a, capital M is a linear subspace of capital N. Okay. Now, this is the direct condition on for subspace. Okay, already we have see and prove the necessary and sufficient part in vector spaces are linear algebra. What is the subspace condition? So that is ax plus by, or here a and b both are field elements and x and y being the vectors. ORR, okay, alpha x plus beta y. Okay, now there is the subspace is also in the linear algebra part W, vector space is capital V, subspace is W. So necessary and sufficient condition is alpha x plus beta y belongs to W of f is contained or equal to V of f. In the same manner, in the normal linear space is capital N and subspace is capital M. So here the necessary and sufficient condition for a non-empty subset capital M of a linear space L of f to be a subspace. Here alpha and beta both the elements are being the field elements. Here x and y both are throughout the linear space elements in capital M. Okay, that is the linear space is L of f or n, whatever it is. So a linear space of the subset, non-empty subset is capital M. So same element series also in capital M is there. So that's why x and y belongs to M and alpha and beta both elements are of the field elements. That's why it can also be written as alpha x, one of the scalar multiplication, beta y, another scalar multiplication. In between the under vector addition is there. So alpha x plus beta y belongs to capital M. This is the direct condition. So what are one step test for subspace or linear space of the subspace, subspace of the linear space. So first of all, necessary condition is proved here. Let M be a subspace of L. Directly we are taking the subspace of the L is there. So then automatically M is a subspace of L means the first of all it is a linear space is there. And the next one, M must be closed under scalar multiplication. Same linear space condition must holds in the under capital M is there. So alpha being the field element and x belongs to capital M and alpha x is also belongs to M. That is the scalar multiplication being the linear space of the part. And same beta and y is also belongs to. So beta y is also belongs to capital M. So we are taking these two scalar multiplications, alpha x and beta y. Okay. So that is alpha x plus beta y belongs to capital M. That is the condition is necessary part. Okay, please stay on the line. Okay, thank you. Okay. Now, this is the necessary part. So, necessary means we are taking the direct condition is there. So, alpha x plus beta y belongs to M. Here, alpha x is the one of the scalar multiplication. Beta y is also another scalar multiplication. So, throughout the under vector addition, here alpha x plus beta y is also belongs to capital M is there. So, the condition is sufficient. Next one. Condition is sufficient. Suppose capital M is a non-empty subset of L is there, satisfying the given the condition. So according to the condition, we are satisfying the linear space is there. Okay. So condition is alpha x plus beta y belongs to M. This theorem is very important in the final examination. Okay. Suppose alpha equal to 1, beta equal to 1. We are getting the result is x plus y belongs to M. Because here x and y, both elements are belongs to M is there. So x plus y belongs to capital M is there. So when the beta equal to 0, we are getting the element is alpha x, given the condition alpha x belongs to M. So that is the scalar multiplication holds good. Okay. Now here x plus y and alpha x both there are two conditions belongs to capital M. Then automatically capital M is a subspace of L is there. That is the simple proof for subspace of L. L means linear space or vector space, whatever it is. Now, this is one of the example of what is the trivial subspace. Trivial means there is the proper and improper subspace. Okay. Let L be any space. See this example. L be any linear space. Linear space itself and subset of L consisting of 0 vector. So, given the linear space of the subset, when it is the 0 vector, it is consisting the 0 vector only. This is the always it is also a subspace of L. These two are called linear space elements and 0 vector. Both are consisting given the subset. So that subspace is called trivial subspace. Set of 0 and itself. Set of 0 means 0 vector. Now and itself means all the linear space elements consisting all the linear space of the conditions must satisfy given the non-empty subset. That is called a trivial subspace. And the remaining other subspaces are called, okay, non-trivial subspaces. Okay, proper and at the same time proper and improper. Okay, proper and improper. So the subspace of L consisting of 0 vector only is called the 0 subspaces. 0 subspaces. So L is the linear space. Those subspaces of this linear space, it is consisting 0 vector is called 0 subspace. So M is a subspace of L and M is the proper subset of L. So M is a proper subset means a proper subspace of L. Only 0 vector is consisting, that is the proper subspace of the part. Okay. Now this is one of the example. 1.6.4. These are subsets of R cube. R cube means that is a three-dimensional part. These are all subspaces of R cube. These examples are consisting the subspaces. First M1 of the first condition is M1. Y coordinate, Z coordinate 0. Here X coordinate is belongs to capital R. So this is the X1. Rectify this one. Okay. Only first coordinate is x1, remaining coordinates are 0. Now, this is also, this vector is consisting, that is the R cube, three-dimensional part. Okay. So, x1 is being the real number. And in the same manner, m2, remaining x1, x and z coordinates are 0. In the replacing y by x2 is a real number. This is also a subspace. Only one vector is there, x3. That is the third coordinate is x3. Remaining coordinates are 0. So, x3 is a real number. x3 is a real number. That is capital M1, M2, M3. These are all subsets. M4 is only first coordinate 0. Remaining coordinates are x2, x3. Those are now they are real numbers. Okay. And second that is M4. M5. X1, X3 is there, X2 is 0. So that is also a M5 is there. M6. X1, X2 is there, X3 coordinate is 0. So that is also a real number. M7. Now we are giving the X1, X2, X3. Now enter the X1, X2, X3 can also be written as there are 7 types of the subsets. Okay, x1, x2, x3. Finally, now these are all real numbers. Some of the coordinates are 0. So these are all, we shall show that M4 is a subspace of R cube. Only M4 is a subspace of R cube is there. This is the M4. Okay. Now, other than M4, we are taking the M4 part is there. Alpha, beta being the real number and XY is also belongs to M4. M4 will be a subspace of R cube means what is the subspace condition? Alpha X plus beta Y belongs to M4. So we are taking the X's. What is the X value in the M4? 0, X2, X3. We are taking the X value. That is the linear element. And another linear space element Y is there. So replacing xy, x2, x3 by y2, y3. So that value is y. So alpha x plus beta y means alpha of 0, x2, x3 plus beta of 0, y2, y3 is there. So from the above subsets, we are taking the M4 set, that is the fourth one, is also a subspace. Okay, 0, we are getting alpha x2, alpha x3, 0, beta y2, beta y3. Finally, alpha x2 plus beta y2, alpha x3 plus beta y3. So first coordinate is 0. So entire this value is also consisting belongs to M4. Same set is also given. Okay, same set, M4 set is given. Replacing x2 by subspace condition. Replacing x3 by subspace condition. Okay, finally given the subset is a subspace of R cube is there. Okay. Now M1, M2, M3 usually called the coordinate axis in solid analytical geometry. So because only one coordinate is there, remaining coordinates are 0. So on the coordinate axis of the part is also A. M4, M5, M6. M1, M2, M3, that is called coordinate axis in the analytical geometry. M4, M5, M6. Now that is also called coordinate planes because just you have to see and refer here. M4, M5, M6. Now, there are only two coordinates. So, plane means plane is consisting at least 2 points or 2 coordinates are there. So, here 2 coordinates are here. Remaining coordinate is 0. So, in M4 and M5, M6. So, that is called coordinate planes. Okay. Now, what is the quotient space? What is the quotient space? Please stay on the line. Now, enter this concept is also, we have learned in linear algebra under UG level and your group theory. Okay. And ring theory in the algebra paper is there. Okay. These concepts are consisting in the algebraic and analyzation paper. So, don't deviate here. What is the quotient group? What is the quotient ring? Quotient space. Okay, quotient space is also consisting in the linear algebra, that is V by W. Okay, but here normal linear space is denoted by N and MBL subspace. Okay, now here normal linear space from the linear space L of F, MBN is subspace. So XB is one of the element, X belongs to L, then the set is denoted by X plus M. Okay, X plus capital M. We are taking the capital M means the subspace of the element is, just you have to see and refer. This is the definition of coset element. Okay, X plus M means small m belongs to capital M. So X plus capital M equal to set of X plus small m. Here small m belongs to capital M. This is called the coset element. Coset of subset of linear space is generated by element is X. Here the X be the generated. So here the coset element is X plus small m. Okay. Now there are so many elements, X1 plus m, X2 plus m, Y1 plus m, whatever it is. X plus m, Y plus m. So X plus capital M equal to set of here single element is small m being the subspace element. So that's why this is the coset element of non-empty coset of subset of linear space. So that is generated by in L generated by small x. Okay. Now here just you have to see and refer this proof. What is the theorem? M itself is a coset of M in L. Capital M means that is the subspace of L itself is a coset of M in L. That is the first condition. Second condition is when the small m belongs to capital M, then automatically small m plus capital M equal to each left coset and each right coset is a coset. Okay, coset is denoted by capital M is there. But here M is a particularly subspace of non-empty subset of linear. So when the left coset, this is small m, you are taking at right side, left side. On right side is capital M plus small m is also equivalent to capital M is there. So just you have to see and refer this proof. We have 0 is consisting of L and capital M can also be written as M plus 0. So that's why M means M plus 0 because 0 being the 0 element in linear space. So at the same time, coset of M in L is there. That is the simple expression of first one proof. And then automatically second one is left or right coset is also a coset. Small m in small m plus capital M contains capital M and small m plus we are taking in any one of the element capital M is small x. M plus x in an arbitrary element is small m plus capital M. That's why here x belongs to capital M is there. So capital M is a subspace of L. So x plus m belongs to capital M. Every element of small m and small m plus capital M is also an element of capital M is there. So capital M plus small m contains capital M is there. Then automatically every element must possess because this is the non-zero element. So inverse is also exists. So m plus of minus m. We are taking the another element capital M is y. So y belongs to m is there. So y and non-zero element is minus m. So y minus m is also belongs to capital M. Okay. And m contains m plus capital M plus small m is contains m. Then automatically capital M contains small capital M contains capital M plus small m. We are taking any element is a small y in capital M is there. Consequently, y minus m is also okay because every element, every non-zero element means inverse exists. So y minus m belongs to capital M is there. So y can also be written as y minus m of plus m. So y minus m means capital M is there. So capital M plus small m. Or small m plus, now this can also be written as m plus of y minus m. So m is also same plus, this element is also belongs to m plus, this element is capital M is there. So that's why y belongs to m implies y belongs to small m plus capital M. Same element in linear subspace of the subset. So y means y capital M contains capital M plus small m. That's why when from the first and second condition, say this is the first equation and this is the second equation. From 1 and 2, we are getting the m equal to m plus m. That is the simple proof. Okay. Now, this condition is applying in the conjugacy. Okay, that is an equivalence part. So, conjugacy relation is also an equivalence relation. Already, we have derived in under UG level, conjugacy classes or conjugacy relation is an equivalence relation. Equivalence relation means reflexive symmetry and transitivity. When these anti-symmetry, when these properties are satisfied, that is called an equivalence relation. Suppose we are taking x and y belongs to L. Because M be a subspace of the linear space. That linear space of the elements x and y is there. What is the condition of is an equivalent under the modulo M. So x minus y belongs to capital M. X minus y belongs to capital M means that is an equivalent modulo M means x is congruent to y and modulo M is there. That can also be written as this is the definition of x minus y of mod M. Means x is congruent to y of mod M. That is the congruence relation is an equivalence relation. That is the question. Please note down. This is the congruence. Congruence relation is an equivalence relation. That is the example 1.6.8. We are taking the three elements in the linear space. First of all, reflexive is there. X is congruent to x. Same element is also expressed in the same part. Okay. X congruent to x mod M means x minus x equal to 0 is also consisting capital M is there. That is the 0 means zero element is also consisting subspace. Second condition, symmetry, x is congruent to y mod m. That is the meaning of x minus y from the definition. X minus y of mod m. X minus y belongs to capital M. That is the meaning from the definition. X minus y can also be written as y minus x belongs to M. Y minus x means that is y is congruent to x mod M. And transitivity, x congruent to y, y congruent to z. This is the definition of x minus y, and this is y minus z belongs to M. So both are adding here. X minus y plus y minus z belongs to capital M. Finally, it can rewritten as x minus z belongs to M. That is the definition of x congruent to z. When these three properties are satisfied, what is that? Reflexive, symmetric, and transitivity. When these three are satisfied, that is an equivalence relation. Okay. Now, when the congruence is an equivalence relation on L, L is divided into mutually disjoint equivalence class. So, when the set of all equivalence class denoted by L by M, set of all equivalence classes denoted by L by M. So, that's why bracket of X means the equivalence classes of the equivalence class is denoted by set of bracket of X and the residue of X. It is also, it read as a residue of X or the equivalence class of X. Okay. So residue, the equivalence class is defined from conjugacy classes. Conjugacy relation is an equivalence relation. That's why bracket of X means residue of X. It denotes the equivalence class. Residue is also one of the special binary operation. Okay. So the equivalence class of X is denoted by bracket of X, and it contains of the element is small x. So we are taking the element is linear space element is y. So y belongs to L means y is congruent to x. This is the meaning of y is congruent to x. And at the same time, y belongs to, what is that? Y belongs to L. Y congruent to x means y minus x is also belongs to capital M. At the same time, we are taking the another element y minus x equal to small m is there because small m belongs to capital M is there. So y minus x equal to means y equal to x plus m is there, small m. So finally, we replacing y by x plus m is there, x plus m set of residue of x or the equivalence class of x equal to set of x plus small m. Here small m belongs to capital M. How to get the value? How to get the equivalence class of this expression? Bracket of x equal to set of x plus small m. Here small m belongs to capital M is there. Okay, this is the coset of the expression. So it is nothing but the coset of m determined by x, that is denoted by x plus m. This is the coset expression. So coset is denoted by L by m under vector addition. L by m under vector addition and scalar multiplication is a linear space. Tomorrow we will show that, we will prove that quotient space is a linear space. This is one of the important question. Don't deviate here. Each and every one is important in the further concept. That's why each and every concept I must explain here. Don't deviate here. If you have any doubt, please contact us and personally throughout my WhatsApp number 9989476833. Okay. If you have any doubt, behalf of the entire this session, please rectify your doubts through the WhatsApp for your doubts clarification. Okay. Now, some other now in the last session, I will give the, yes, there is no doubt. I will give the some other important concept of functional analysis in the examination point of view. Don't worry. Don't bother about this here because this is one of the important session, especially this is the online classes. You're very useful for your preparation. Okay. If you have any doubt, please contact my number. Once I have to repeat, now this is the last, I am giving that number is there, 9989476833. This is my WhatsApp number. If you have any doubt, please contact us and personally through WhatsApp for subject point of view. Thank you one and all. Wish you all the best and wish you good luck. Okay. Any doubt is here? Tomorrow we will discuss the quotient space. The set of all cosets is a linear space. Okay. The quotient set of the elements are denoted by x plus capital M equal to, or set of x equal to, bracket of x equal to, or the equivalence class of x equal to set of x plus m. That is the x plus m is the coset of this part. All the cosets represented throughout the set of all cosets is a vector space or linear space. At the same time, normal linear space condition. So that's why quotient space, how to form the quotient space. Tomorrow we will, tomorrow means next class, we will explain from this part. Okay. Thank you one and all. Wish you all the best and wish you good luck. Okay. Are you any doubt? Hello? Who is K? Students, please respond here. Okay, thank you. Thank you, thank you. Thank you one and all. Okay. We will meet again next class. Okay, thank you.